What is refraction and why does it happen? This video will explain refraction, or the bending of light, in terms of three different models of light. The ray model shows us that light moves in straight lines and will go through each other unaffected. Light rays also help explain how mirrors and lenses work. On the other hand, the wave model of light explains that light moves like a wave and can diffract through openings or interfere with other light waves. Finally, for quantum mechanics, the photon model shows us that light can also behave like a particle called a photon. This Feynman diagram shows how an electron can absorb or emit a photon.
The ray model of light represents how we experience light in our day-to-day lives. This model functions best for apertures or openings of 1 millimeter and larger. This model says light travels in straight lines called rays, indicated by arrows. Each arrow represents a multitude of parallel rays that move in the same direction. Rays do not interact with each other in space. However, light rays do interact with matter. They might reflect, refract, or be absorbed depending on the circumstance. Light travels at 299,792,458 meters per second in a vacuum. However, that speed changes depending on the medium that the light is entering. This is indicated by the index of refraction, represented by little n. The index of refraction measures how much light slows down in any given medium. This table is just a sample. This speed change in the ray model is seen as a change of direction of the ray. Here, at 0 degrees from normal, you can see there is no refraction. However, if you move the ray to 25 degrees from normal, you can see that the ray is refracted. As the medium changes, the angle changes due to the fact that the speed of light is changing. Then, once we get to the same medium, air and air, there is no refraction because the index of refraction has not changed and therefore the speed doesn't change. Mathematically, we show this change in speed and direction through Snell's law seen here. You can see the two angles are compared with the speeds of light in the two different media and the two different indexes of refraction. In this diagram, you can see the first angle is measured from normal in the first medium, and the second angle is measured in the second medium. We more commonly see this as n1 sine theta 1 equals n2 sine theta 2, where n is the index of refraction for the first medium, theta 1 is the angle of the ray in that medium, measured from normal. n2 is the index of refraction for the second medium, and theta 2 is the angle of that ray in the second medium, again from normal. As an example, this shows a low index to a higher index of refraction. n1 is 1, theta 1 is 25 degrees, n2 is 2, and theta 2 is what we are looking for. Starting with Snell's law, we plug in some numbers, divide both sides by 2, take the arc sine of both sides, and come up with a 12.2 degree angle for theta 2. And that's what we're looking at right here in this diagram. You can see the angle is refracted. For example B, it is a high index to a lower index of refraction. n1 is still 1. Theta 1 is what we are looking for. n2 is 2. Theta 2 equals 25 degrees. Again, with Snell's law, plug in the numbers, divide both sides by 1, take the arc sine of both sides, and that will give you a theta 1 of 57.7 degrees, which would look something like this.
The ray model may work well to explain refraction, but it can't explain other observable characteristics of light, such as those highlighted by the double slit experiment. Things like interference and diffraction patterns, etc. The wave model of light, on the other hand, can easily explain these observations, along with things like reflection and refraction using Huygens Principle. Considering the wave in 2 dimensions makes applying the principle more straightforward. Imagine a transverse wave traveling from left to right as shown in the bottom right-hand corner of the screen. Each crest of the wave corresponds to a wavefront shown above it, almost as if you were looking at the wave from a bird's eye view. Let's take this diagram and flip it vertically to show the wave coming from the top down. The Huygens Principle states that we can consider each wavefront to be a source for an infinite number of secondary waves. The secondary waves radiate out from each point along the wavefront in a circle. The line tangent to the secondary wavefronts shows the location of the new wavefront. In this case, it's parallel to the initial wavefront. Using the Wolfram simulator, we can see this play out. Here, it shows the waves traveling from the bottom to the top. And you can see that along the secondary wavefronts, they eventually form a tangent, showing you where the next crest of the wave would be. So how does this apply to refraction? We're going to use Huygens' principle and consider the same two examples that we saw in the ray model section of the video. We're going to use the same incident angle of 25 degrees with the same indices of refraction, meaning that our refracted angles should end up being the exact same, 12.2 degrees for the first one and 57.7 degrees for the second. In the first example, the index of refraction of the second medium, shown here in blue, is twice that of the first. Watch how the waves slow down in the second medium, and how the secondary wavefronts form a tangent that is bent from the path of the initial wave. Here, we overlay the ray diagrams from the first part of the video on top of the model, and we can see that the ray model of light is just a shorthand version, showing the consequence of the waves traveling in both medium. We can also show this for example B, where the second medium is now half the index of refraction of the first. Notice the change in the wave's speed as it passes between the blue and yellow sections.
Okay, so I believe you that light appears to act that way, but I kind of need to know a little bit more about why. So if each photon is living its best life and basically can go in any direction it wants, why does it look like it follows those rules? Let's say that you are sitting on some beach and you see a sea turtle caught up in some plastic bags. Oh my god, we have to save the turtles. You can get to her by taking a bunch of different paths, all different combinations of running on the sand and swimming in the ocean. You want to get to her really quick. So how do you know which path to choose? And which path is going to be the quickest? How does light know which path to choose? Some very smart people have done tons of math that we could sit here and look at, but yeah, I'm going to pass on that. So this Feynman character came up with a way to use, wait for it, multiple representations to explain it. So I say let's do that. Here's how it works. The idea is to represent the probability that an event can happen with an arrow. The arrow's length, compared to some arbitrary unit of 1, will be so long that its square will equal the probability. Oh, and these arrows spin. The speed it rotates at is related to the wavelength of the light. So a blue clock hand will go around faster than a red clock hand. Now for this example, we have a bunch of different paths. As the photon is emitted from a source and heads down a path, the arrow turns. When the photon hits the detector, that path's arrow stops. You add all of these arrows up, tip to tail, and you get a final amplitude. These paths at the end make a swirl, and adding them up, they cancel each other out. So yes, all paths contribute to the probability, and the photon can and will travel along all possible paths. Let's look at a photon refract as it moves from air to glass. Light doesn't really only travel in straight lines, but for this we will focus on paths with double straight lines. As the photon is emitted from the source and moves along its path, the clock arrow begins to rotate. When the photon hits the glass, the photon slows down, and the clock continues to rotate at the same speed as before. When the photon hits the detector, the clock for that path stops spinning. Each arrow represents a path, and its direction represents the path's path integral. At the end, you will add them all up and get a final amplitude. This is the probability that when a photon is emitted from a source, a photon will hit the target.